afternoon, and thank you for joining us. Today's webinar is Start the New Year Off Right, USP 643 System Suitability, and Joy Osborne, who is our TOC Product Line Manager, will be presenting. We will be taking questions at the end of the webinar, so feel free to submit those throughout the presentation, and Joy will address them at the end. Okay, I'm going to go ahead and turn it over to Joy.
Okay, thank you, Shelley. Hello, everyone. I want to start off by wishing everyone a happy new year. I can't believe it's already 2018. And thanking everyone for joining this webinar today on United States Pharmacopoeia Method 643, which is part of the system suitability check. The reason I chose this topic was that the method USP 643 recently changed to include sterile water levels, which are at 8 parts per million. Originally, the method only included 0.5 parts per million carbon, so now it includes both 0.5 and 8 parts per million carbon in the method. And just a little bit about Teledyne Tekmar, if you guys don't know already, we are a manufacturing company that manufactures volatile organic compound equipment, including purge and trap and headspace. We also do total organic carbon, obviously, with this webinar today. We do 2 types of TOC analyzers. We have UV persulfate analyzers, which is what we're using today, which is called the Fusion. And then we have catalytic combustion TOC analyzers as well, which are the Lodix and Torch. We also carry semi-volatile organic compound chemical instrumentation that does sample prep and extraction of catchers, which is a pesticide method. We've been actually developing TOC instruments since the 1960s through the Dorman name, and we are the market leader in purge and trap. All right, so let's start off with the agenda. So today's agenda will be, we'll talk about the process of validation of analytical instrumentation using the DQ, IQ, OQ, PQ process. We'll talk about USP 643, of course, the requirements, the purpose, and how, to help you pass those requirements. And then the challenge for today is, can sterile and bulk water be run on the same calibration curve using the Fusion? So can that 0.5 ppm carbon and that 8 ppm carbon be run on the same calibration curve? Of course, that would save you time of running and make it easier for you as well. And then we're going to discuss the results that I got from running method 643 on the Fusion. So here's the process of validation in the pharmaceutical industry, which is called the DQ, IQ, OQ, PQ. DQ stands for design qualification. That's actually the part we do. So during the designing and developing of the product, like the Fusion, there are numerous array of tests that we do. We do a ton of analytical testing, including, of course, like a range testing, minimum detection limit testing, longevity of testing, so how long that calibration curve will stay in calibration, precision and accuracy, and then we do different types of carbon compound testing analytically. We also do a lot of, longevity testing of our parts to see how long we can run them until they fail. So we'll, run a pumper, simulate 10 years of use, that kind of thing. So that's all part of the DQ part. So you guys don't have to worry about that. And then there's the IQ, which is the installation qualification. So these are all the things that go into the setup of the instrument. So making sure you have the right gas. So for the Fusion, you need nitrogen, and you need at least 99.99% purity for it to run. Things like that. Make sure you have the right electrical setup, the right computer for it, and the right documentation, including manuals, spare parts, standards, certificate of analysis, those type of things. And then that leads us to the operation qualification section, which ensures the instrument is operating correctly. But this is more the physical testing of the operation of the instrument. So this is making sure the auto sampler arm is moving correctly, the syringe and pumper are moving correctly, that kind of part of the instrument is functioning. And then we move to the PQ, which is the performance qualification section. that it ensures that the instrument can perform all the essential tests it needs. This should be done periodically, so you should be doing it. It depends on your SOP, but at least once a year or something like that to make sure that your instrument is still running like it's supposed to be. And the system suitability test, or USP 643, is part of the PQ process. So that's how it fits in there. Just talking about the Fusion a little bit, the Fusion also has an automatic OQ operation qualification part built into it. It has something called benchmarking, which is a self-diagnostic test. It basically goes through all kinds of different tests. It tests the lights, it tests the beeper, it tests the movement of the arm on the auto sampler, making sure it goes to the right spot. It tests the valves, make sure they click on and off correctly, that the detector is reading properly, that the syringe and pumper are moving properly, and it also checks for leaks. So that can be part of your OQ if you just want to run a easy benchmarking test. All you have to do is hit start benchmark and go through that process. Also, with the OQ part of it, you want to check and make sure that the data is archiving correctly. That's definitely part of 21 CFR 11 compliant. With the Fusion, you can have it automatically archive. As you can see here, it's not checked, but if you check this box, you can set it to do it like every day or every week or whatever you want it to, and you can have it go to any network drive you want to. Also, you can create permissions, which are like profiles for each analyst, and allows them to do certain functions within the software. For example, if you have somebody new that's perhaps an intern or something, you would uncheck a lot of these boxes and maybe they could only start a schedule. But somebody more advanced user is able to do everything. They can edit methods, create new methods, edit blanks, that kind of thing. So we do offer an IQ, OQ, PQ with the Fusion. That is an option. One of our service engineers will come out and they perform a series of tests. One of those tests is a calibration curve, of course. So they check the linear regression value, to make sure that is good. The M value or the slope value, make sure that's high enough that you're getting enough response from that detector, and the B value is low enough. The B value represents the background of the instrument. So if that's high, that's signs of contamination, things like that. They also do a reagent blank analysis. So that includes checking, making sure your sodium persulfate and phosphoric acid solutions are clean enough, and that the line from those solutions is clean enough. They do a specificity challenge. So with that, they use inorganic carbon to make sure it doesn't interfere with the organic carbon. It should have less than 1% interference. They also run check standards against that calibration curve to make sure it's running accurately and it's staying in calibration. They do a cross-contamination challenge, which is basically they run a reagent or a DI water sample after a high-level standard, and they see how much is carried over into that water. And then they do a LOD-LOQ test, which is limit of detection and limit of quantification. So that is a theoretical value. For this test, they run 7 replicates of a reagent blank water, and then they apply that T value. If you want to learn more about detection limits, I have a separate webinar about that would fully explain it and how to calculate it. That is on YouTube, so be sure to check that out. And then they do a system suitability test, which is USP 643, that we'll be talking about today, which is running those sucrose and 1,4-benzoquinone standards. And then they do IntelliDilution test check, which is a feature that Fusion has. If you run a sample that's above your calibration curve, it will flag it. It will dilute it back into calibration range for you, which is a great feature. If that happens overnight, you accidentally get a sample that's higher in carbon than you suspect it to be, and it's above your calibration range, you'll still have results in the morning, which is really nice. And then we do a user manager validation to make sure you can assign properly those permissions we talked about, and then archive validation. But you can also do these tests if you'd like to as well, but we do offer that service from our service engineers if you're interested. And these are the things I suggest users to continually check as part of the PQ process. Of course, you're going to be running your calibration curves. I usually run a check standard every day, and I run the check standard at the beginning of my schedule and the end of my schedule. I know some SOPs say every 10 samples or X amount of samples to run a check standard. I usually do it at the beginning and at the end. And as long as those pass, I know my calibration is still good and the results in between those check standards are still good. I also run a blank every day. Again, that verifies that your system's not contaminated, or your acid solution or sodium persulfate solution is contaminated. So just checking to make sure everything's clean and good to go. And then I do like to do a system suitability test about, I would say, every 6 months to a year. Run a USP 643, just make sure that it's oxidizing those compounds at the same rate. And I'll, of course, talk about that more later. All right, so here's the explanation for USP 643. It's to test the system's ability to oxidize different organic compounds. So when you calibrate with KHP, that's not really telling you if different organic carbon compounds will be oxidized at the same rate. So it's just ensuring that it will oxidize every carbon-containing molecule in your matrix. Like I said, there's 2 levels now to it. There's a bulk water level, which represents water for injection, purified water, water for hemodialysis, condensate of pure stream. There's also a sterile water, which represents sterile water for injection, sterile purified water, sterile water for irrigation, and sterile water for inhalation. It's required to do system suitability testing for pharmaceutical industry. It's suggested in other FDA industries like cosmetic and personal care, and I have seen an uptick in people using TOC instruments in cosmetic and personal care industries. Again, that's a good way to check and make sure that water that you're starting off with is very clean, free of bacteria, free of contaminants, or anything else that could harm a consumer. All right, so let's look at the comparison of the bulk water versus the sterile water under USP 643. So they actually have 2 different limits of detection. The bulk water one is 50 ppb, and the sterile water is 100 ppb. With the Fusion, you should have no problems achieving the 50 ppb limit of detection. It has a very, very low, very accurate, low-level sensitivity. For the reagent water, it's also 2 different standards. For the bulk water testing, your reagent water should come in at less than 100 parts per billion, while for the sterile water level testing, it should be less than half a ppm. Honestly, if you're having problems getting below half a ppm on the Fusion, you have other problems. You have some major contamination, your issues carry over, bad reagents, something's going on. You should never have that high a level carbon in your water. And then we have the sucrose and 1,4-benzoquinone for the bulk water. It's at half a ppm, while the sterile water is at 8 ppm. And then we have the percent response efficiency, which is basically the ratio of 1,4-benzoquinone to sucrose that has to come out between 85 and 100% of each other. So maybe they come out as close as possible. Again, that's measuring the fact that they're oxidizing at the same rate. With that said, let's look at these different compounds. So on the left is sucrose, which is represents your easy to oxidize compound. So you should have no trouble getting half a ppm or 8 ppm as a check standard for sucrose. Your KHP is what you usually calibrate with. It's in the middle of how hard it is to oxidize. And then you have your 1,4-benzoquinone, which is their difficult to oxidize compound. You can see by the chemical structure why it would be harder to oxidize. It looks like a very stable, very strong structure with its benzene ring and double bonds and things like that. All right, and here's the formula given in USP 643. It's 100 times, which makes it a percent. Your 1,4-benzoquinone minus the reagent water response, ratio to your sucrose response minus your reagent water response. And it looks kind of complicated, but when you slice it down, it's pretty easy. All right, so the challenge for today is, can the fusion perform sterile and bulk water analysis on one calibration curve accurately? I do want to emphasize that this is not required by USP 643. There's no mention of you have to run it on the same calibration curve. You could easily run a low-level curve and then a higher-level curve if you want. The only reason I did that is it's just easier to do, and it reduces your calibration time. You don't have to run 2 calibration curves to do this testing now. A little bit about the fusion, which is what this test was on. The features of it are, it has auto calibration. So basically, and I used that feature for this, is it will take a stock standard solution and make serial dilutions. So it basically makes the calibration curve up for you. You don't have to pipette anymore, which is great. It saves time. You can, if you're busy, you have time to do other things in the lab, and it's also very accurate. I dare say it's more accurate at preparing or diluting standards than I am. That's always the challenge. It's very, very good at diluting. It also has the IntelliDilution feature, which is what I talked about earlier. If a sample's above your calibration curve, it will dilute it back down into that calibration curve for you. You don't have to be present for that, so you'll still have those results at the end of the schedule. And then it has a mass flow controller, which allows for higher flow rates between samples. So that helps with the cleaning up of the system between sample runs. It also helps with reduced gas consumption. It can automatically shut itself off with no use. And then, it has other features like it helps enable features like leak checking, things like that, which is great. It's also 21 CFR Part 11 it's a tool for compliance, which is great if you're using it for the pharmaceutical industry. If you don't know what it is, that means you're not in the pharmaceutical industry, but if you know what it is, it's in the pharmaceutical industry. Basically, it's an electronic signature system. So if you change a method or anything like that, it will record it for you. That way it tracks everything for you. It has pre-programmed methods. That TOC pharmaceutical method, I use that all the time for low-level analysis. It's great. It works, I would say, 80% of the time for applications, for low-level applications. However, in this case, I did optimize the method. I did alter the method. So, and I will talk about how I changed the method to get that 0.5 ppm and 8 ppm in the same calibration curve. And it has automatic shutdown, which, uses less gas, so it's less costly. All right, so before you get started running 643, it's really, really important, I can't emphasize this enough, to have a clean, well-operated system. So I always start off the day with a couple cleans, if I haven't run it in a while, and a reagent blank. And what a clean does, it actually pulls a volume from the DI reservoir, so you don't need to use a sample or anything like that. And it cycles that water back and forth between the IC sparger and UV reactor 3 times. So you'll actually get 3 reps for the TC side. So let's look at that. So here's an example of running a clean. The first system is dirty and the second system is clean. And you can tell that by the results. So for example, the first TC clean should be less than 15 ABS counts. So this should be less than 15. And by the third time that water cycles through, it should be less than 3. So this is a sign of a dirty sample, but it's still cleaned up. But I would still run another clean to verify that this first number came down. And then here's an example of a clean system. Again, the first TC clean should be under 15 ABS counts, and the fourth should be under 3 ABS counts. So here's an example of a good system that's ready to run method 643. Okay. And then I also said it's good to start with a blank, and this checks your reagent and your acid values to make sure those are clean. Your reagent blank should be less than 15 ABS, which in this example it is, it's 4.46. Your acid blank should be less than 3 ABS, which it is. In this example, it's 1.09. Okay, so if this value, if the reagent blank is above 15, that's a sign that your sodium persulfate solution is contaminated. And I have to say that I definitely had a few lots of sodium persulfate come in that were high in carbon. And so just keep an eye on that. That seems to be the most notorious place to get contamination is from sodium persulfate. It's much less likely to get it from your acid, your phosphoric acid, but it can happen. It could even be, you know, the jar that the solution is in could be contaminated. Maybe it wasn't washed well, something like that. So just keep that in mind and keep an eye on that as you run the fusion. Okay. So now let's talk about the method parameters we use to run this method USP 643. Here is your standard TOC pharmaceutical water method. It uses a 9 ml sample volume. It doesn't do any dilution. But if you look here, it gives you an optimal sample range for that method, which is only up to 6.7 ppm. Now remember, we're trying to get 8 ppm in that curve, so you know right off the bat that this method will not work for 643. So, you know, there's a couple things you can do to increase that upper end of the calibration range. So of course you could use less sample volume, so you can just increase this value here, or you can increase the dilution. So both things put less sample into the system, so there's less carbon, going into the detector. So it makes the detector have a bigger range. So that's exactly what I did. I changed the sample volume from 9 mils to 4.5 mils. And now my optimal sample range is up to 13.4. I calibrated up to 10, and I wanted to give it a little extra room just so I get a nice sharp calibration. So I did play around with this value a little bit, and I came out that 4.5 worked the best. Again, for each system, that might be a little bit different. You might have to play around with this value a little bit too. Maybe it'll be 5 mils on your system, maybe it'll be 4 mils on your system. You have to kind of play around and try different methods for it. I also, just to help with carryover and keeping the system as clean as possible, and just something I've picked up by running the fusion, is I like to turn this UV reactor pre-rinse on, and I like to use a volume that's bigger than the sample volume. And that just gives them a little bit extra clean in between each sample. So it's just a little helpful tip you can use really in any method. It's not going to hurt it to do a little extra rinse of that UV reactor. Okay, so that's the method. There's something I really love about the fusion. It makes USP 643 really easy to run, is it already has a system suitability standards thing in the software. So you can edit it too. It defaults as the reagent water must be 100 parts per billion, which it talks about. You could change it to 500 ppb to do that other testing as well. but I like to keep it at 100 because really your system shouldn't really be operating above 100 parts per billion. The fusion doesn't typically have reagent water coming back above 100 parts per billion. And the response efficiency should be between 85 and 115%, which is what the method says. You do have the option to change it, but if you want to follow 643, you should not change that. All right, and here's the schedule I set up, just an example of what I was running. So like I said, I like to start with a clean and a blank. Clean, make sure the system's clean enough to run it. A blank, make sure my reagents are good to go. And then I ran my calibration curve. You can see how I used the A slot, which is from those middle stock calibration bottles, which are really great. They're bigger bottles, so you can get a lot of more reps out of them. So I ran 0.1 ppm, 0.5 ppm, 1 ppm, 5 ppm, and 10 ppm in triplicate using the method I created, which I just called 643 Pharma. You can call it whatever you want. And then I ran a DI water sample after the 10 ppm, just in case there was a little bit of carryover, since I immediately after that ran the reagent water sample that, remember, has to be less than 100 ppb. And then I ran my 0.5 sucrose, my 0.514 benzoquinone, and then my 8 ppm sucrose and my 8 ppm 1-benzoquinone. I did put another water sample in between there. It's just DI water. Okay. All right, here are my calibration results. You can see here I got a really great R-squared linear regression value of at least 3 nines. I like to get at least 3 nines, but it's up to you SOP-wise. You know, a lot of labs only require 995. I usually strive to get 3 nines, which is very easy to do with diffusion. Also make sure that the B value is never above 8. If you have an 8 as a B value, that means there's too much contamination in the system. So, you know, keep an eye on that. Make sure it's nothing above 8. Okay. And then here's my bulk water results. Remember, these are the 0.5 ppm results. So here's the reagent water. It must be less than 100 parts per billion. It's at 14, so definitely under 100 parts per million. It passed. And then we got our sucrose and 1,4-benzoquinone. And those are ratioed against each other using that formula. So when you apply that formula, which the software does for you, it calculates 97.75%, which is definitely between 85 and 115%. So it did pass. I also like to do an added check. It's not written in 643 to make sure that these results are within 15% of your KHP standards. So that means it should come out very close to your 0.5 on your KHP, which it is within 15% or 85% to 115% of that standard. All right. So let's talk about it. If the results had turned out differently and that reagent water was too high, I would recommend checking the source of your water. I know here we use very high level reverse osmosis water. I strongly suggest something like that. Of course, the better the quality of your water, the lower that's going to be. But with that said, I know you got to stay on top of keeping your filter replaced and all that kind of stuff. If you let it go, even a really great system, if you don't replace those filters or do preventative maintenance, your carbon will start to come up in it. So it's good to keep an eye on it. And then also check and make sure the cleans are passing. So the cleans would help show if there's contamination or carbon in the liquid sample pathway of your system. All right, so sterile water results. So this is the 8 ppm check of sucrose and benzoquinone. For this, when the software was written, of course, this wasn't on the software, so I just set these up as check standards. But that works great. You still, though, will have to calculate it yourself, so I just ran the math real fast. So it's, this response minus the reagent water, which was 14 ppb, and then this response minus the reagent water, and they're ratioed against each other, times 100 to give you a percentage, and it was 107.01, which is well within that 85 to 115%. Interestingly enough, the sucrose did come in higher than the 1,4-benzoquinone. If you remember what I said earlier, sucrose is an easier to oxidize compound than 1,4-benzoquinone. You didn't really see this phenomenon at 0.5 because there's not as much carbon as the sample. So this takes a little more time, a little more effort to oxidize an 8 ppm than a 0.5. So you can start to see that pattern with these results, even though they pass. So I thought that was pretty interesting. But if you wanted to get these closer, it's passing. But if you do want to get these closer, you can play with the oxidation factor. So basically, you're going to allow the things that help that 1,4-benzoquinone to oxidize. You're going to increase those. So, for example, you could increase your sodium persulfate amount. So this is part of the reagent volume. The default method had 0.8 mils, so I upped it to 1.4 mils. Okay, so that is going to put more sodium persulfate in that chamber with your sample to help that oxidation process along. And you can also increase the time the sample is in that UV reactor with the sodium persulfate. And that's with this pre-sparge time. It defaults at 0.2, and I upped it to 0.6. So those are the type of things you can do to help that along. But really, with the default parameters, we were able to help it oxidize. I do want to remind people that the UV lamp is a consumable. They usually last a very long time. In fact, I have had them last even 10 years, but sometimes after a couple years of use, they'll fade. So obviously, if the lamp's fading, which is helping oxidize it, that could be contributing to that discrepancy between the sucrose and benzoquinone. Okay. Now, if the 1,4-benzoquinone is too high, much higher than the sucrose, well, there's no really chemical explanation for that. So sometimes it could be as simple as the standard was made wrong. So I just suggest remaking the standards and starting again and calling tech support, because the 1,4-benzoquinone should never come out higher than the sucrose. It can come out the same, or very close, but it shouldn't be dramatically higher than the sucrose, because that wouldn't make any sense, because it's a harder to oxidize compound. You could also call our tech support. We have a great tech support group that's here, so they would be more than happy to help you guys. So in conclusion, the Teledyne Tekmar Fusion UV persulfate system ran USP method 643 bulk and sterile standard concentration using one calibration curve, which allows you to save valuable analysis time.